We left off on our overview of Lab 9 looking at this diagram showing carbon dioxide levels for the past 10,000 years. 10,000 years ago is here, and the present is here. And this is mostly a record from ice core data, so this is what we call proxy data. It's not measured by an instrument, but we take little samples of ancient atmosphere out of ice cores, and we can get the carbon dioxide levels out of them. And then the modern instrumental record we've talked about is right here, part of the Keeling curve. And so you can see that in the past 10,000 years, carbon dioxide levels have remained somewhere around 260 to 270 ppm, and then today they are skyrocketing. But the last ice age ended about 10,000 years ago. So what about prior to that? Is there anything different that happens during ice ages? So we can actually go back as far as 800,000 years with proxy data. And this is what it looks like. This is 800,000 years ago to the present. And again, we are up here today. Everywhere you see a peak is where there was an interglacial, meaning the time period between a glacial event, and it was a warm period. Remember that carbon dioxide is a greenhouse gas, so when there's a lot of carbon dioxide, the greenhouse effect is more intense and the climate is warmer. When carbon dioxide levels are lower and the greenhouse effect is less intense, the Earth gets cooler and ice forms. So when the levels of carbon dioxide are lower, the Earth was glaciated. We had an ice age. So here's an ice age, here's one, here's one, here's one, here's one, etc. And so you can see there's a periodicity of interglacials and glacials, interglacials and glacials. In general, the interglacials never reached any higher than maybe 300 ppms through 800,000 years of history. And again, today, we are up here. So when people tell you, well, Earth has natural variations in its carbon dioxide levels, that's very true. But you have to distinguish the natural variations, which we have a record of, compared to the variations that are going on today. The other three options down here are future scenarios, which are quite interesting, and I will let you explore those on your own. So back to the lab. Part B of this first section of the lab asks you to look at this figure. And this is where those monthly variations occur that I've mentioned before are related to seasons. Now I told you it's very difficult to kind of tell which month each of these little red dots corresponds to. Wherever you see the year, that's where January occurs. And then 3 months later, the little tick mark would be April, etc. But if you recall what we looked at in the last video, in general, the peak moment of carbon dioxide levels tends to occur in May, and the lowest points tend to occur in October. So use that information to help you answer these two questions here. And then finally, summarize everything that you've learned so far about carbon dioxide in the atmosphere. So that's the first part of this exercise completed. Now we're going to move on to carbon dioxide in the oceans. This part, you're going to watch a video that's going to tell you a little bit about the roles of phytoplankton and zooplankton in the ocean. When you get to this part down here, it's going to tell you that the ocean has two processes that pump carbon dioxide into it. A physical carbon pump, which does not involve any biological processes, and then a biological carbon pump that involves living organisms. So this part up here is a preview to the biological carbon pump, which is described over here. This first part is the physical pump. You're going to read this information that describes this chart right here, and then answer a few questions related to it. One of the big key points you want to see here is that the red numbers in this chart indicate the amount of carbon that's come from human carbon dioxide emissions. So those are important numbers to understand in this diagram. Another really important thing on this page is that there's a major typo in one of the multiple choice questions. So number 12, the choice A shouldn't say 92. It should say 2. Now, why would I tell you there's a major typo if the typo isn't in the actual answer, right? I wouldn't tell you there's a major typo if the answer was one of the incorrect answers. So I'm basically giving you the answer to number 12 here. But if you've already tried the lab and you've looked at number 12 and you've said, you know, I don't see the right answer here, it's because it wasn't there. Okay, so replace the 92 with a 2, and hopefully that will make a lot more sense. Then you'll examine the biological carbon pump, which again is related to what you watched in this video. And you'll finish with a couple more questions. So now we've looked at the carbon dioxide in the atmosphere. We've looked at how that's placing more carbon dioxide in the oceans. And in our last section, we're going to look at how that makes the ocean water become more acidic. We're going to start with looking at the pH scale. Some of you may be familiar with this, some of you may not. The pH scale runs from 0 to 14. The number 7 in the middle of that scale is neutral, meaning it's not acidic and it's not basic. As you move to smaller numbers, you become more and more acidic. And the entire scale is actually logarithmic based on the concentration of hydrogen ions. And what that means is if something is a pH of 5, then it's actually 10 times more acidic than something that's a pH of 6. If it's a pH of 4, it's 100 times more acidic than something that's a pH of 6. So every time you go one number down, it's 10 times more acidic than the previous number. And you can see some of the things that are listed here. Coffee, wine, orange juice. Now, how many of you like a good old Coca-Cola once in a while? Coca-Cola is fizzy because it has carbon dioxide dissolved in it. When carbon dioxide dissolves in a liquid, it makes it very acidic, which is sort of the whole point of this lab and the problem with the ocean. Coca-Cola has a pH of 2.5, way down here. So keep that in mind, that relationship between carbon dioxide and acidity. The other end of the scale is basic. And so things that are up here are not acidic, but basic, or sometimes it's called alkaline. So you're going to look at the scale and answer a few questions about it. And then you're going to watch this 6-minute video called The Once and Future Corals. And there are 2 questions to answer about it. One is on this page and one is on the next page, so I've kind of put them there together. In your own words, describe why corals and coral reef communities are valuable to people. And you might even not realize that they're valuable to people. You might think, well, they're pretty and maybe scientists like to study them. But they actually provide important resources for some people in the world. And then also, how are human activities negatively impacting coral reefs? And if you want to learn a bit more, there is a fantastic documentary that's on Netflix for free. So if you happen to have Netflix, you can watch it. It's called Chasing Coral. It's about an hour and a half long. And in 2017, it came out. It won all kinds of film awards. It was shot with over 500 hours of underwater photography, with more than 500 people involved. There were more than 30 countries involved in this filming, and it's all about the same idea of coral disappearing because of ocean waters becoming more acidic. Finally, the last page brings us to this graph right here. And in some ways, this is a graph you've already seen. This is the Keeling curve in red, with carbon dioxides in parts per million here and years right here. But now we're adding some more information. We're adding a blue data set right here, which is the carbon dioxide values from the ocean water measured up here at Station Aloha. And here is where the Keeling data are coming from. And so this is also using the scale on the left of carbon dioxide levels. Now the blue points are the data points, and you can see that they're very, very scattered compared to the Keeling curve. And there's been a best fit line placed in here. So these data are much more variable, but still they do show a trend. We've also added green data points, which is the pH of the seawater out here at the Aloha Station. So these measurements you can see began in about 1990. The pH uses the scale over here with 8.1 to 8.5 sort of capturing the range here. So what you're going to do is you're going to answer the questions that are on the page. According to the figure, how does rising carbon dioxide levels in the atmosphere, which is the red curve, correlate with carbon dioxide levels in the ocean, which is this blue set of data? In other words, are they related? Do you see any trends? In the same figure, how does pH of the ocean change as more carbon dioxide accumulates in the ocean? And so that's comparing the blue and the green curves. And then finally, you're going to summarize the trend of the changing pH in the oceans and why it's of a concern. So that's it. We've gone from convincing ourselves that there is indeed more carbon dioxide building up in the atmosphere, and that's leading to more carbon dioxide in the oceans, which is leading to more acidification of the ocean waters. Good luck with the rest of the lab, and please come see me during office hours if you have some questions.